Okay. Hello. We wait actually for. Can you hear me? I hope you can hear me and you can see my shared desktop. I can't hear anybody here. Okay. Can you hear me? Hello? I hope you can hear me and you can see my shared desktop. Okay, just wait for a few minutes to others to join, and then let's I do the presentation, and that the presentation will be recorded. Yeah, would you please update me that if you can hear me clearly?
Yeah, we can hear into your screen.
Okay, great. Okay, I start the presentation, and actually the presentation is being recorded and will be shared, of course, on Canvas, and you have access to this later on. The presentation was CFD with open source software called OpenFOAM. I'm Ardalan Javadi, part of Mechanical Engineering School of Georgia Tech. The CFD actually is the matter of solving continuity and Navier-Stokes equation, momentum equations, and but at first place, Navier-Stokes is second order nonlinear partial differential equation, and another obstacle is there is no explicit equation for P. So we need to overcome these two obstacles to be able to solve these two equations together. Anyhow, solving these two equations, the unknowns are P, which is a scalar, and three components of velocity vector. So in total, 4 unknowns and 4 equations. So the system of equation is closed, and mathematically we should be able to solve the equation, but we need to overcome those two obstacles first. From Navier-Stokes perspective, from CFD perspective, actually not very many viscous fluids. When we say viscous, it means that the dynamic viscosity playing role. Not very many viscous fluids are solved analytically, so we need to actually run CFD. The field of CFD is maturing fast. With many commercial software tools available, it is possible now to achieve approximate but realistic CFD results for a wide variety of complex 2- and 3-dimensional viscous fluids. What you see in this presentation is about OpenFOAM, what applications are, installation, environments, and aliases, brief discussion about finite volume code, which OpenFOAM is an example of it, simple algorithm, which is a way of coupling pressure and velocity. We jump into tutorial. Very first tutorial is cavity fluid. We go to post-processing, overview of what we have conducted, and a more, in fact, fun and cool tutorial, motorbike. We go to post-processing and PowerFOAM. Beforehand, it's assumed that actually you have some basic knowledge of Linux, and you already installed it, sorry, on your machine, and you know what's going on with the environments of OpenFOAM. Actually, I give brief description of environments and aliases in this presentation, as I said. And the version that we've worked with is OpenFOAM 23.12, which is just released in December 2023, last year. Applications, solvers, and utilities. Actually, OpenFOAM is a C++ library. Solvers are each considered to solve a specific physics through continuum mechanics equation. And utilities are designed to perform tasks that involve data manipulation. So solvers and utilities are being used for pre-processing, post-processing, and post-processing. So special applications for pre and post-processing are included in OpenFOAM. Converters to from other softwares are available. To from tens of softwares, almost any engineering software that you can imagine. You can import and export data to from OpenFOAM to those softwares. And in fact, very soon when you get expert in OpenFOAM, then you can modify and actually develop your own application. OpenFOAM is distributed with a large number of applications, but soon any advanced user will start developing new applications for own special needs. The basic way to do this is to find and copy the application that almost does what is needed, and then to modify it by copy paste from other application that has some features that are needed. So before everything, of course, we need to install OpenFOAM. OpenFOAM is based on Linux, and the version of Linux that I use is Ubuntu. If you use Mac or Windows, of course, appropriate versions of OpenFOAM are available. But first, you need to install Linux on your Windows machine, for example, then compile Windows version of OpenFOAM. So as you can see here, just simply you can. This is, as I said, based on Linux Ubuntu version, and just the link is provided in the slide in the presentation. Just click on it, and it directs you to the OpenFOAM ESI version. And this ESI version go to download Linux, Mac, Windows. I use Linux, but if your operating system is different, just pick the nice one. To Linux, and my version is Ubuntu, and these data are provided in the slides. That's the same what you see here in the slides. So just I go there, and so OpenFOAM, in fact, just open a new terminal in Ubuntu, and then copy the first line. So it starts downloading and briefly compiling, updating repository and compiling OpenFOAM. So it takes few seconds or short time. And actually, we go through these 4 steps, then OpenFOAM 23.12 will be available. So let's wait for it. And if you have any question, please interrupt me. And if you're gonna do the assignment, which is optional, but it has really good points for you, please interrupt me if anything is vague. So the second line, okay, good. Connection speed is fine, and this line is just compiling OpenFOAM. Sudo means super user apt-get installed OpenFOAM default. Just wait for this to be done. Yes. And in the meantime, a presentation on YouTube is recorded and shared with you that is basically the same. So you can actually go there and see what's going on. Okay, OpenFOAM is compiled now, and just if I type on command line, I type OpenFOAM 2312, then OpenFOAM is available. Right now I have OpenFOAM. Just if you write, for example, IcoFOAM, then my IcoFOAM is a solver of OpenFOAM. In the following of the slides and presentation, I will explain what IcoFOAM is. So as long as it reads IcoFOAM, so the OpenFOAM is installed appropriately. So let's go to the presentation and next slide. This is on Windows. If your operating machine is on Windows, click on this install. It directs you on the same website, installation on Windows 10, and then just in fact follow the instruction step by step. As I said before, you need to first install Ubuntu, then OpenFOAM on Ubuntu. So I skip these two lines, but the information is provided in these two slides, and of course on the website. In fact, that's taken from the website. For parallelization, for post-processing and visualization of the case that you have calculated, an open source software called ParaView is necessary, and that's easily installed on your machine. Click on this link. It directs you to the ParaView website, and you have different version sources: Windows, Linux, Macs. I use Linux, but if your operating machine is different, just pick the appropriate one. The Linux, click on the latest version. That's about 700 megabyte. It takes it's being downloaded. When that's downloaded, just unzip it and use it. That's very easily doable software, although in old time it was very different. I still wait for ParaView to be downloaded. Complete. Just go to where that is downloaded. That's downloaded here. Just I extract it, unzip it, or extract it. Okay, it takes some time to be done. And then in bin folder, there is ParaView, executable ParaView file. And in this folder, open a terminal and just do ParaView. And then you have this visualization software. So that's done. Everything is actually ready to be used. So let's back to the presentation. Just a point is when you open ParaView like this, you are not in the case that you have calculated in the folder of your case. So you need to touch a .foam file in that directory wherever you are, and then open that .foam file with ParaView. We will do that later on, and I will show you how the procedure. Environments and environment variables. When you compile OpenFOAM and gonna load OpenFOAM to use it, you source bashrc file. This bashrc file sources settings automatically. So all settings of OpenFOAM are set now. And it loads a lot of environments. For example, what environment means? For example, on the command line, write on the terminal that your OpenFOAM is loaded. In fact, here we installed OpenFOAM. Here, environment pipe WM. Okay, so it gives all environment. What my OpenFOAM is, GCC is a compiler, precision is double precision, the directory, the way that it parallelized Linux, and so on and so forth. So a lot of information about that. For example, if I'm gonna see the environment that includes foam and the different directories that includes foam, just I say env pipe grep foam. For any exact environment, you can echo that, echo foam app, for example, and it offers you exact directory of user lib OpenFOAM, OpenFOAM 2212 applications. And in that directory, there are a lot of information about the solvers, the utilities, and the boundary conditions, so on and so forth that you need for CFD. Aliases. In aliases, in fact, that's a shortcut to direct you to correct place if you're gonna touch or copy or study any specific file for any application. Useful aliases in OpenFOAM are src source, which direct you to foam src, lib library, run, which is working directory, foam src, foam finite volume, application, utilities, solver, tutorial, and foam third parties. Any of them, it means that if on the command line I write source, it directs me to the appropriate directory. It means that in fact all source files of OpenFOAM located at this directory. When I say tut, it directs me to tutorials. So all available tutorials are here: heat transfer, Lagrangian, incompressible, the combustion, DNS, Lagrangian, multiphase. So if you're gonna study or learn more about any of those cases, you can go to those locations and copy what you want, and in fact go through that. And a major recommendation is make your own run application source directory using make directory minus p parent w project user. This user can be any name, usually your name, directory run application source, and then copy the source file of OpenFOAM here and then modify it or improve it. That's risky to touch the original file of OpenFOAM, because if you're going to run another application, then it may need the original file in the existing form. Then actually it may interrupt or make some trouble for you. And there are a lot of other information about OpenFOAM, how to program it, how to develop it, how to learn about that. And if you are interested, you can go through the links provided, or the directories, or this program guide PDF file, which is located in the installation of OpenFOAM. Finite volume. What finite volume code? OpenFOAM is a finite volume code. So it means that the cell width volume V is connected to some neighbors, and the value of any variable, P pressure, T temperature, these two are a scalar, V vector velocity, are located at the centroid of the cell. And any cell is connected to some neighbors. Here, just one neighbor in the right is presented as N. If that's two-dimensional, usually, not always, P is connected to 4 cells, left, right, top, and bottom. If that's three-dimensional, that's usually connected to 6 cells, right, left, top, and bottom, front, and back. And definitely they are connected. Any phase connects to the 2 cells. So the mass flux through any cell will linearly change through this cell, and the way that each cell is connected to its neighbors called numerical scheme. So continuity equation and momentum equation will be solved. As I mentioned before, 4 unknowns, 4 equations are available, but that explicit equation for P and linearizing momentum equation should be done. This is, in fact, icofoam, simple foam, and piezofoam are 3 solvers for incompressible fluid fields in open foam. Icofoam is for laminar, transient fluid. Simple foam is for turbulent, steady state fluids. Piezofoam is for turbulent, transient fluids. So depending on your application, you can pick appropriate one. If we write momentum equation, we're gonna actually linearize it first, and then here at the bottom find an explicit equation for P called Poisson equation. So for linearizing it, if we write the momentum equation in this form, so in fact move everything to the left hand side of the velocity except pressure gradient. Mu, u is the velocity. Mu equals minus nabla p. Here m is just coefficient matrix of the velocities. Now, what most algorithms, means simple, piezo, and more, do is convert this sparse matrix M. A sparse matrix means a matrix with a lot of zero components, into a diagonal and off-diagonal matrix. So we change we change this M to AP and HU. AP is diagonal, easy to invert. HU is off diagonal. So we move H to the other side of the equation and then divide both sides to AP. So the Newman momentum equation is linearized in this form. UP equals HU divided by AP, which is the invert of AP, minus nabla P divided by AP. HU is what HP is in this form, known by calculation from previous iteration of the velocity or initial condition. If that's first iteration, it uses initial condition that the user V introduce. The first term, this term, represents the matrix coefficients of neighboring cells multiplied by their velocity, while the second part contains the unsteady term and all the sources except the pressure gradient. Okay, so right now we simplified, or we linearized, not simplified, sorry. We linearized the Navier-Stokes equation. Those two obstacles are overcome. This is continuity equation. Nabla inner product of vector u equals S surface, all surface from two neighboring cells, dot UF. This is P point, centroid of the volume. F is face of the volume. So we need to exchange this P and F. So UF is like this. Then inner product of this equals 0. And the Poisson equation will be in this form. The first term equals the second term. You see here. Equals sigma S surfaces. This is actually the same. So that's Poisson equation for the pressure. Right now we have an explicit equation for pressure. What simple algorithm does is simple loop. From the first guess, with initial condition that we introduce a P pressure and U velocity. With those U that we introduce, HU and AP will be updated. We use these coefficients in the, and P we introduced as well. So we have everything. Actually, we guessed everything. We use this in the momentum equation, which does not satisfy the continuity, and we find the U. With this U, we update these two coefficients, and we put it into Poisson equation, and we find a new P. This P satisfies the continuity equation. We replace this P into the momentum equation, and then we resolve it. We find a new U which does not satisfy the continuity equation. And like this, iteratively, we continue to find a U and P which satisfies the continuity equation. The pressure correction is used to obtain the correct velocity that satisfies the continuity equation. But wait, no longer satisfies the momentum equation now. It means that if you are here, it doesn't satisfy the top one, and other way around. Again, momentum equation is solved with the updated pressure and velocity field. Update UP and AP, HU and AP. This needs to be iterated in a loop until the solution converges. So this is what OpenFOAM does when we use simple form. Let's go back to the terminal. This is the folder of simple form. In fact, where simple form is compiled in OpenFOAM. Simple form, and this is simple. In fact, follow these folders. The others are actually some folders inside of simple form for other applications. Simple form.c, simple form U equation, which is momentum equation 1 in the slides. Simple form is a loop, simple loop. U equation, momentum equation. Here, P equation 2, Poisson equation, and here create field is, as long as we are coding it, we need to introduce our U and P, or if there is heat transfer or anything else, other variable need to be introduced. So create field is for introducing the variables. So simple form, first equation 2, and introducing the variable. This is the way that sorry, OpenFOAM actually be getting, in fact, working with different loops and different actually different theories. Let's go to tutorial and use what we have learned. The first case is IcoFoam. As I mentioned, IcoFoam is a laminar transient case, cavity tutorial. And a link is provided here. If you click on it, it directs you to the OpenFOAM website with more details about that. This is the cavity fluid. Is a cube with 3 sides wall and 1 side moving wall within 1 meter per second from left to right, ux equals 1 meter per second. Any side is 10 centimeters. The origin is located at the bottom left. So depending on the kinematic viscosity, we can control the actually the Reynolds number. So this is the place that the tutorial is located. We will copy that and we will run it, and we will know about that. Mesh generation. We need to generate a mesh, which means discretizing the computational domain to be able to solve the equations. So that's a cube, 1 block cube with 8 vertices, vertex 0 to vertex 7. And in a dictionary, in system folder, we need to introduce that to be able to generate it. Scale 0.1 means we put, for example, here 1, and then it scales it to 10 centimeters. So that's not 1 meter, it will be 10 centimeters. So vertices, 8 vertices at 8 points, and I'm not sure if I forgot to say, as long as if that's 2-dimensional, we introduce a 3-dimensional cube in OpenFOAM, but front and back are introduced as empty boundary conditions. Other 4 direction, left, right, top and bottom, need actually they are in touch with different cells. So We introduce a block coming from 8 vertices, and the way that it rotates is important. 0, 1, 2, 3, 4, 5, 6, 7. So counterclockwise. The number of cells in each direction, 20 in X direction, 20 in Y direction, and as it's two-dimensional, 1 cell in Z direction. In total, 400 cells. Introducing boundary condition, moving wall, which is a top boundary coming from a face generated from 4 vertices, 3, 7, 6, 2. 3, 7, 6, 2. And the way of direction is important. Again, that is counterclockwise. So we call it moving wall. Other 3 walls called fixed walls, so coming from 3, in fact, 3 set of vertices generating 3 faces. So one of them is 0, 4, 7, 3. So 0, 4, 7, 3. We generate this left surface, and we put no slip boundary condition, which is a stationary boundary condition. Let's continue. And front and back is empty as long as that's two-dimensional. Scale. I thought when you run block mesh, it generates the mesh. And so let's go back to the case, run it, and then come and talk about boundary condition and initial condition. Okay. These are the slides, and you can actually you have it. So let's open a new terminal. Yeah, actually, I believe that you have generated your own run directory, your user run directory. Run directory, and then I copy the cavity. Here I have the cavity. Let's enter cavity. So in any case, in OpenFOAM, you have 0 directory, which is initial condition, constant, which includes transport properties for kinematic viscosity. When we generate mesh, here a folder called polymesh will be generated, so which exists contains the mesh, and system folder, black mesh dict for mesh generation, control dict to control the simulation like time step, writing intervals, and so on and so forth. Schemes for numerical scheme, the way that the cells are connected together, and FV solution, which for doing the solution procedure. So let's follow. We are the 3 that here. Actually, we check this. Let's run block mesh. Right now we have the mesh with 400 cells, the number of points, number of faces, and number of internal faces. Patches 0 to 1, 3 patches. So moving wall, fixed walls, and front and back. Let's do check mesh. So the quality of the mesh getting checked. 400 number of faces, number of internal faces, 3 boundaries, and my domain, the quality of non-orthogonality and skewness are very important. So the mesh is okay. When I said that touch a file, let's say cavity, it can be any name, but .foam is important. When I touch it, then I have a cavity.foam. We open this in ParaView. So let's go back to the previous directory where when we had ParaView will be opened, and then here and we go and find the cavity case. So the cavity.foam is here. I open it, cavity.foam, apply, and this is my cavity. The top boundary, 3 boundaries, and the cell inside. Here, surface, 2 surfaces with edges, and 400 cells, 20 cells in each side. Here, right now, we haven't run it yet, so we don't have any result. So, and front and back are empty as long as these two dimensions, just one cell in Z direction. Okay, let's run it. And write the output in log file. That's running in the background. And that's done. And this time or these directories are generated, which is 0.1, 0.2 seconds. So the data are written into it. For actually update the case, refresh, and then here we have time steps. Go to the last time step, and then P and U are here. Let's say to U, and this is meter per second, 1 meter per second as the top boundary is from left to right, and this is the domain. And in fact, it gives a vortex here. And this is P. There is a expansion in the left and contraction on the right, as long as the velocity is from left to right. And for doing post-processing, we go and check the vectors of the flow. Here, glyph 1, and then orientation array U velocity and scale array pick U velocity. And then click on apply. Let's make it unseen, and here it shows in fact the vortex inside of the cavity, which is rotating like this. Let's go back to so here boundary and initial condition. As I mentioned, there are P and U. In zero directory, there are P velocity, P pressure, and U velocity. This is pressure. Dimension is a square meter divided by a square seconds. As long as this is incompressible flow, it means that P divided by density. Initial condition, we apply 0. You can put whatever you want. 0 means 0 relative pressure, atmospheric pressure. Boundary condition, boundary field. Moving wall 0 gradient, fixed wall 0 gradient, front and back empty. So what is talking about zero directory P? It talks about this. And P, volume scalar field. Velocity, volume vector field. U velocity, meter per second. As long as that's vector, 3 components are necessary. So we pick a stationary initial condition. The top wall is 1 meter per second, X component, no slip on other 3 sides, and empty on front and back. Then we run it, and actually we did it, so the results are ready. So let's continue, and this is the way that we do post-processing and how we use ParaView. What we have done is we will have a look at what we did when running the cavity tutorial by looking at the case files. First of all, it should be noted that Icofoam is a transient solver for incompressible laminar flow of Newtonian fluids. It means that the kinematic viscosity in transport properties in constant folder is constant. The case directory originally contains the following subdirectory: 0 initial condition, constant system. After our run, it also contains the output, this plus log, which is the output of the simulation. The zeros directories contain the values of all variables at those time steps. The 0 directory is thus the initial condition. The constant directory contains the mesh and the transport properties dictionary for the kinematic viscosity nu. The system directory contains settings for the run, discretization schemes, and the solution procedures. The Icofoam solver reads the files in the case directory and run the case according to those settings, to the setting that is introduced in system folder. Another case which I'm gonna show you is a motorbike, which is a turbulent flow. We run it in a steady state case to keep it simple. So appropriate solver will be simple foam and motorbike. The inlet velocity is 20 meters per second. The mesh will be generated using SnappyX mesh, and which is another way rather than block mesh. Run steady state solution. The flow is turbulent, so simple foam will be solved, and the computational domain in total will contain about 400,000 cells. So my domain is a rectangular cube. Inlet, outlet, top atmosphere, bottom ground. Sides are usually cyclic or sleep. Different boundary condition can be applied, and motorbike at the center. And as you can see, the mesh is finer around motorbike to be able to resolve the flow field. Okay, just we conduct these instruction step by step. We copy the motorbike tutorial to our run directory. As long as we are in run directory, so we are in run, we enter our motorbike. So inside of motorbike, this is the folder inside of it. So we are here. You have copied the tutorial and moved to foam run motorbike. Now copy the motorbike surface and convert it to OpenFOAM format to generate the mesh. Copy this line. So the surface is copied into constant 3 surface. Change the format of the surface to something which can be read by OpenFOAM, and then run BlockMeshDict to generate the cube, the rectangular cube that I showed you before. The rectangular cube contains this amount of cells, points, faces, and the size actually, and this is the size of the box. So we're gonna generate a mesh using the SnappyX mesh, and it takes a while. It takes a few minutes. Just in meantime, I'm gonna say that if you have any question, just interrupt me, and I will be happy to discuss about that. But you will have an optional assignment, which is a viscous laminar flow around an airfoil, and that's in fact, for doing that you need to install OpenFOAM on your own machine, and then be able to run it and work with BlockMeshDict slightly, and then post-process it. Of course, you need ParaView too, and then analyze it and write a report. And that's pretty good, and it gives you pretty good understanding of the flow field and how actually flew around an airfoil and separation from an airfoil through an adverse pressure gradient works. So I'm still waiting for this SnappyX mesh to generate my mesh.
I have a question.
Yes, please.
So for our project, do we have to create our own U and P files?
What do you mean about UMPY?
For the for like the simple foam, like setting the whether or not it's no slip, or like setting the
actually yes, as long as the flow is laminar, the zero directory is empty, and you can create your own P and U, and yes, you need to apply your own boundary conditions, but a case is provided for you. In fact, follow the hint and it will help you. In fact, in the bottom, in the PDF file, in the bottom of that assignment, a hint for another airfoil is provided. Go through that link, which is available tutorial in OpenFOAM. Go through that and provide very useful information.
Ardalan, could you share your screen with that PDF and then show exactly where you're referring to?
Sure. Okay, you actually received, Dr. Aiden, do you have my screen? Do you have the PDF file?
Yes, yes, we can see your screen now.
Yes. Actually, here, empty directory of 0, constant, and system folder, and here there is a hint, and which is about another airfoil, and just it has a link. Just click on it, and it directs you to a very similar airfoil. And here there's a lot of information, files, and yeah, you can actually learn from it. Actually, you can run this case as long as you install OpenFOAM. You can run this case. You can learn a lot from this. The assignments is very similar to this.
Okay, thank you.
Yeah. So the way that this would work is that you know, you first listen and go through these tutorials, and then once you follow the assignment, then you may get into points that you don't know what to do or something is not working. And Ardalan is going to have office hours,
Sure.
that then regular office hours, in fact, that then you can contact him and have sessions with him to ask your questions. And then he will help you along so you can move along in the project.
Okay, sounds good. Thank you.
Okay, sure.
And the last thing that we did, actually, as long as that motorbike, I'm back to the slides. That motorbike case is slightly heavy, 400,000 cells, and we need to run it in parallel. So I just prepared it for decomposing my domain, and I ran decompose par. I copied it here. I ran decompose par, and then here I divided or distributed my computational domain into 6 processors. Right now, in my case folder, I have 6 processors. Then the last thing that I will do is run it there. MPI run number of processor 6, simple form -parallel, write it the output into log file. Just run this, and yeah, it takes probably another few minutes. I'm not sure why. I don't know why it doesn't run. Okay. Actually, I tried it many times. Probably something is wrong. Oh. Yes, sorry. I haven't copied the zero original in the. Actually, the initial condition was not introduced, so I haven't done this line. But yeah, just I copy from 0 original to have 0 directory. Then let's parallelize it. Then run the case. Okay, that's running. Okay, right, and it takes a few minutes. So later on, when the case is running, as long as that's transient, so this it gives very stationary solution, and then as long as that's parallelized, we need to reconstruct from different processors. reconstruct it from different processors, and I do a simple post-processing, which is actually generating Q criterion. This Q criterion actually shows the vertices around this motorbike, and I will show you in Parafoam, or in fact, don't be confused with term Parafoam or Paraview. Both of them are the same. So let's save some time and touch that motorbike.foam file and open it in Paraview. This is motorbike. This is the file that I touched. And this is the cube that we generated with BlockMeshDict. Let's add some opacity, decrease some opacity. And in the center, we are not in the center, in the middle, motorbike is there with refined mesh around the interest region, let's say. And this is inlet, outlet, sides, top and bottom. Bottom is ground and top is atmosphere with 20 meters per second at inlet. And let's check the processors. That's 200 time steps are done. Let's continue with this. As I mentioned, if I gonna actually be able to read my result, I refresh my case and the results are available then. So 200 U velocity, and here I'm gonna take a slice at the center of my bluff body, my motorbike. I'll toggle down. And this is the velocity in the wake of my, this is the velocity in the wake of the motorbike. The velocity deficit in the wake of the motorbike. And you can check pressure, and there is actually contraction in front, expansion at some points, and yeah, you can actually do some post-processing and visualization around that for generating the vertex, the Q criterion. So Q criterion at all time steps are generated. Go back to the Paraview again, refresh it to have that Q which is generated. And then we have Q now. For watching the Q, go to contour by Q, and take isosurface value of, for example, 50, and then apply. Let's visualize it with, for example, velocity to be more visible. And this is the vertices in the wake of the motorbike. These two large vertices are getting generated from the biker feet, and the top one, this one, is coming from the bike hip. And this is the way that you can proceed, actually study any case that you want, and learn about the calculated flow field. It was my presentation, and any question is welcome.
Okay, are there any questions for Ardalan? I know that this is a lot of material that you have heard, and this is all new for you. That's completely understood. But don't worry. I mean, you will start gradually, and again, there is a lot more information that you can get from the video tutorials on YouTube. That's part of the assignment that you can go through. And then once you get more and more familiar with the software, then you can ask questions and hopefully download the software and try using it. Are there any questions at this point? Okay, all right. Ardalan, please, let's discuss your office hours. What times can students contact you if they have questions, and then we will post it on Canvas for the students.
Sure, of course.
Okay.
I will update you. Sure.
Yeah. Okay, all right. Last chance to ask any questions. All right. If not, then hopefully we can post the recording of this on Canvas, and so you can look at it again. Okay, take care, everyone. Thank you for participating, and thank you, Ardalan, for going through the material here.
My pleasure.
Thank you.
Thank you. Bye.
Bye-bye.